Welcome to Lesson 2. In this lesson, we will start with an introduction to cryptography and cryptanalysis. You will learn the different encryption and hashing algorithms. You will also learn the details about public key infrastructure, or PKI, and certificate authorities. Also, you're going to learn about the process of certificate enrollment as well. In this lesson, we will also cover examples of SSL, TLS, and IPsec implementations. Cryptography or cryptology is the study of the techniques used for encryption and secure communications. So basically, cryptographers are people who are studying and analyzing cryptography to, again, protect communication and basically protect different areas of information security like data confidentiality, integrity, authentication, and also non-repudiation. There are so many implementations of cryptography nowadays. You have things from like VPNs or virtual private networks, which you're going to learn a lot more about them later in the course, or e-commerce, secure email transfer, the credit card chips that you use every day. And probably you're actually using cryptography right now to listen to me over potentially a web connection using the Transport Layer Security Protocol, or TLS. So you're going to learn a lot more about the different cryptographic algorithms later in the course. Another concept that the exam expects you to know is what is cryptanalysis. And it's basically the study of how to crack encryption algorithms and their implementations. You also have to know what is a cipher, right? And a cipher is a set of rules or a recipe, which can also be called an algorithm, that it will dictate how to perform encryption or decryption. And there are literally hundreds of encryption algorithms available out there. And in the next lesson, you're going to gain an understanding of the different or the most popular encryption protocols in the industry. So a cipher is basically a set of rules or a recipe that can also be called an algorithm about how to perform encryption or decryption. And there are literally hundreds of encryption algorithms available in the industry, and there are likely many more that are actually proprietary and are used for special purposes like governmental use and national security and some other ones, right? Or probably by the time that I actually recorded this course, there may be others that may be introduced in the industry, right? However, what I want to introduce here is the most common methods that cipher use and the algorithms that are actually used, across the industry, and that, of course, you will see in the test and the exam. Now, one of the most common methods that ciphers actually use historically is substitution. And this type of cipher, substitution cipher, will, just like the word says, substitute one character for another one. For example, a simple substitution cipher can actually change a letter from an alphabet with another letter. And to make it more challenging, we can actually shift more than just a single character and only choose certain letters to substitute. Also, you can actually shift and rotate, across that alphabet. And this actually has been an assistance since, probably for over 3,000 years, right? As a matter of fact, there's actually some elements in history, like the Caesar cipher, right? That was actually a method of substitution to actually literally encrypt or decrypt data, to obfuscate data and have at least a secure communication channel between two entities. Another type of cipher is a polyalphabetic cipher, and this is actually similar to substitution, but instead of actually using a single alphabet, it can use multiple alphabets and switch between them by some trigger character in the encoded message. Then you also have transposition, and that method uses many different options, including the rearrangements of letters, just like in the example that I have in the screen here, and where this message, if you actually read it from top to bottom and left to right, it just says, "This is secret." Now, there's also the concept of a key or a key pair, right? But first, let's actually start with just a single key, right? A key is actually the instructions on how to reassemble the characters, in a substitution environment or a substitution cipher, or in a more complex environment, right? At the end of the day, that key is truly that recipe on how to actually perform that reassembly or encryption, right? And then both parties will actually have to, agree on that key. Now, a one-time pad or OTP is actually a good example of a key that is actually only used once. If you use that method, basically you want to, let's say, encrypt a 32-bit message, then we use a 32-bit key, also called the pad, which is used one time only, and each bit from the pad is actually mathematically computed with corresponding bit information from the message. You also have the concept of block and string ciphers, and a block cipher is basically a type of symmetric key cipher, and symmetric means that the same key is actually used to encrypt and decrypt data. And a block cipher basically operates on a group of bits at a time called a block, right? Thus the name a block cipher. And within this type of encryption, the key to encrypt is actually used also to decrypt the message. So it's only one key in this environment, right? Now, examples of symmetric block cipher algorithms include the Advanced Encryption Standard, or AES, which is actually the preferred method of all the ones that I'm showing here. But the predecessor of AES was the Triple Digital Encryption Standard, or Triple DES. You also have DES, which is the Digital Encryption Standard, and also IDEA. Now you also have stream ciphers, and a stream cipher is also a symmetric key cipher, meaning that the same key is actually used to encrypt and decrypt data, where the plaintext data to be encrypted is actually done one bit at a time against the bits of the key stream, also called the cipher digit stream. Now the resulting output of this implementation is called the ciphertext stream. Hashing is a method used to verify data integrity. So for instance, you can actually verify the integrity of a file that you download from the internet, let's say a software image file from Cisco.com for any of the Cisco products, or your favorite game out there, or an image file, or any type of file, right, for that matter, and to make sure that it hasn't been modified by either an attacker or it hasn't been corrupted because of some flaw. Now, there are two hashing algorithms that have been very popular, for many years. One is called MD5, which is actually, a legacy algorithm and should be avoided, and we'll get to that in a few minutes. And then the other one is SHA, and SHA has different flavors of it and different versions, and different key lengths, right? So the higher the key length, the stronger the algorithm will be, right? So you have things like SHA-512 and so on, right? Now, you don't have to know every single permutation of the SHA algorithm and everything else, but what you need to know is which one is more secure, but I hate to say secure, stronger is a better term, than the other one. So what I did is actually I created a GitHub repository that has a whole bunch of different algorithms and which ones you should avoid and which ones are recommended. And Cisco also has the same information and a little bit more in a website that I'm actually sharing the screen, on where not only you can see the different hashing algorithms, but also encryption algorithms that are on the internet and their usage, and whether you should avoid them, whether they're legacy or they are actually next generation encryption algorithms. So definitely take advantage of this resource. Now, a few things about HashSF. Hashing is a one-way function, right? And they can be used for many different things, as I mentioned to you, to verify the integrity of files, but also for the integrity of communication. Like, for example, protocols that you're going to be learning later, like IPsec, it uses actually hashing to verify the data that is in transit between two IPsec enabled devices. Now in this example, what I'm doing is actually I'm creating 3 different files, and the contents of each of the files are different. And what I'm doing is I'm using the SHA-SUM utility. It's a Linux utility that you can actually use to verify to make a checksum of those files. And basically that checksum is a specific value that is calculated for each of the files, regardless of the actual name of the file, right? So since each of the files have different contents, as you can see in the screen, the value, the checksum of the files, in this case using the SHA algorithms, are different. However, if I actually copy one file to another one, let's say file 1 to file 3 in this example, now I'm copying the whole contents of file 1 to file 3 and overwriting file 3. So if you can expect that if I actually run this again and I run the checksum, you see that now they are the same despite that the file names are different. So this is a very simplistic example. Of course, there's so many different use cases for using hashing, but this one actually illustrates it so you can actually truly understand what hashing is all about. So as I mentioned to you before, symmetric algorithms are the ones that actually use one key, right, for both encryption and decryption. But also you have asymmetric algorithms. And in this case, you actually have something magical about these asymmetric algorithms, is that actually they use a key pair, and then mathematically they will work together to be able to actually encrypt and decrypt data. So for example, in this example, of course, I have 2 entities that they actually want to communicate between each other, and I have Derek and Hannah, and the attacker here that is called Eve wants to try to eavesdrop the conversation between Derek and Hannah. And in order for Derek to actually send an encrypted message to Hannah, he needs to obtain the public key of Hannah, right? So think about that. This is actually implementation, public key implementation, such as PGP, or Pretty Good Privacy, which is actually used to encrypt email, or S-MIME, or many others, right? So in this case, again, whenever Derek wants to send an email, an encrypted email to Hannah, he needs to actually have her public key, and she can distribute this public key in many different ways, right? Using many methods, like just sending it over email, or posting it in a website, or giving it personally to him, and so on, right? And one of the most common types of key distributions for things like PGP and S-MIME is actually to have the public key in services like different repositories, like MIT has one that I'm showing in the screen. Also, there are tons of different key servers. There's a service called Keybase, and as a matter of fact, this is actually my Keybase profile, on where you actually can see my public PGP key, right? But now going back to the example, Derek wants to send an email to Hannah. Now that he has the public key, he will encrypt that email using her public key, and then whenever Hannah receives the email, then she will decrypt that email using her private key, which she will never share with anybody. And of course, if that key is actually compromised, then she will revoke and invalidate that key, and then will generate a new one. And that revocation process also applies to digital certificates. So the exam, I'm not going to go over all the different details of cryptography, but at least I'm going to cover some of the things that you must know for the exam. And you have to know what are certificates, right? Which are actually used for many different purposes. Like I just cover one for S-MIME that actually uses certificates, which includes public and private key, concepts. And then also, websites and web applications, they actually use certificates to be able to encrypt data from a browser to an application, or between APIs, right? So they're used for many different implementations, even including VPN services, and you're going to learn more about that later in the course. A public key infrastructure basically consists of programs and data formats and communication protocols, security policies, and public key cryptography mechanisms that will work together in a comprehensive manner to enable a very wide range of dispersed entities. It can be people, it can be systems, to communicate in a secure and predictable fashion. So in other words, PKI establishes a level of trust within an environment to perform secure communications. There are several PKI standards in the industry, but the most popular is the ISO authentication framework that actually uses public key cryptography and the X.509 Standard. Now, PKI provides authentication, confidentiality, non-repudiation, and also integrity of the message that are actually being exchanged. There's a little bit of a difference between the public key cryptography and PKI, right? So public key cryptography is another name for asymmetric algorithms. However, PKI stands to much more of that. It's actually an infrastructure, right? It's an infrastructure that assumes that the receiver and the identity of the receiver can be definitely ensured through things like certificates, and that an asymmetric algorithm will actually automatically carry out the process of the key exchange. Now, within PKI, there are a lot of different entities, including certificates, certificate authorities, digital signatures, and so on. And in the next lesson, you will learn a lot more about certificates and certificate authorities. As we mentioned in the previous lesson, certificates are one of the most important pieces of a PKI environment or a public key infrastructure. Now, a certificate is the mechanism that is used to associate a public key with a collection of components in a manner that is actually sufficient to uniquely identify that owner of that such certificate. Now, the standard for how the certificate authority creates certificates, you're going to learn more about what is a certificate authority and registration authorities in a few minutes, but that standard is the X.509 standards, and actually that dictates different fields that are actually used within the certificate and values that are used to validate, or in other words, to verify the validity of that certificate. Now, certificates include things like serial numbers, version numbers, identity information, the algorithm that is actually being used, the lifetime of the certificate, when was it issued, and also when will it expire, and there's an expiration date on the certificate. It also includes the signature of the issuing authority, in other words, the certificate authority. Now, there's also the concept of the registration authority, or the RA, and the RA performs the certification registration process. It establishes and confirms the identity of either the individual or a system, and then it initiates the certification process with an CA, with the certificate authority. And it does that on behalf of an end user or a system like a web server and so on. And it also performs certificate lifecycle management functions as well. Now, how this registration process takes place is that the user makes a request to the RA, and then the RA requests certain identification information from the user, and then copies that information into a registration or a certificate request, and it's actually sent to that CA, to the certificate authority entity. Now, the CA creates a certificate with the user's public key, and again, it can be a system too, that doesn't have to apply to a user, and then the identity information is actually embedded within that certificate, right? Now, going back to CAs, certificate authorities, there's the concept of a root CA, and a root certificate authority is the one needed in order for you to be able to actually assign certificates and generate certificates for users and systems. However, in most environments, you have a hierarchical deployment where you actually have a root CA and you may have one or more subordinate CAs. And this can actually be on a very hierarchical way, many different levels. So the subordinate CAs may have other, subordinates as well. And another best practice in the industry is that you can take the root CA offline to prevent that root CA for being compromised. Now there's also a certificate revocation process, and the certificate revocation process, that's whenever you are invalidating that a certificate is no longer valid. So think about that you have a user within your organization, and that user leaves the organization. He gets a job in a different company, or it can be a system as well. It can be a system that is now retired, and you want to delete, quote unquote delete, but invalidate that certificate. And whenever you do that, that's whenever we call it a certificate revocation process. So whenever you revoke a certificate, you actually keep track of the serial number of that certificate, and you can put it in a file called a CRL, a certificate revocation list. Now there are protocols that have been created to perform the certificate validation process, along with CRLs. And one of the protocols is the OCSP protocol that is actually used, across the industry, fairly pervasive. So a thing to keep in mind is the security of certificates is not so much of actually issuing them and registering, entities in a secure manner, but also to make sure that the validity of that certificate is correctly done, and that whenever you revoke a certificate, that validation process is adequate and sufficient. Let's go over what is Transport Layer Security, or TLS. This is actually a widely adopted security protocol that is pretty much everywhere, right? Again, you probably are using it right now, listening to me through a web browser or through any secure application. Now, the primary use of TLS is actually encrypting the communication between a web application or this web server to a browser or to a client. However, it is also used in many other applications, especially in application programming interfaces or APIs for machine-to-machine communication. Also, it has been used in email, in different messaging applications, voice over IP implementations, and of course, TLS or SSL-based VPNs, which actually leads me to the next topic, right? So what is the difference between TLS and the Secure Socket Layer or SSL standard, right? TLS actually evolved from that standard, from that Secure Socket Layer standard or SSL, which was actually developed back in the day by Netscape. And in the beginning, of course, TLS version 1 began development as an SSL version 3.1, but the name of the protocol was actually changed before publication in order to indicate that it was no longer associated with that a prior protocol, and that it addressed a ton of vulnerabilities and enhancements in that protocol. Now, many users also ask, what is the difference between TLS and HTTPS? HTTPS is actually an implementation of TLS encryption on top of the HTTP protocol. Now, which is actually used by pretty much most websites nowadays. And any website that actually uses HTTPS is basically just employing TLS encryption and TLS technology. So why should you use TLS, right? TLS encryption can actually help protect a web application from attacks, or an API, from man in the middle, and from attackers to be able to actually obtain sensitive information. At the end of the day, encryption addresses confidentiality. So how does TLS work? TLS can be used on top of the TCP, right? Transport layer. And there are three main components of TLS: encryption, authentication, and integrity. And of course, you already know that encryption hides the data being transferred from attackers, and authentication ensures that the parties exchanging information are who they're claimed to be. And then integrity verifies that the data actually has not been tampered with or has not been changed in transit. Now, a TLS connection is initiated using a sequence known as the TLS handshake. And for your reference, I actually have the TLS handshake here in the screen. And basically, after the client establishes a TCP connection to the server, in this case a web server, The client actually sends a hello message, or a TLS hello message. Then the server will reply back with its hello and certificate information. And then the client performs the client key exchange, and also they agree upon the cipher that will be used. So the algorithm, the encryption algorithm that will be used for the encryption and the encrypted channel. And then of course the server actually verifies that, and if it complies, it actually finishes that handshake and replies back to the client. Then of course that's actually a part of the negotiation. After the negotiation takes place, then all the data will be encrypted. Later in the course, you're going to be learning about VPNs, and not only SSL-based VPNs, even though they are still being called SSL, they're based on TLS, of course, but TLS or SSL-based VPNs, and you're also going to be learning a lot more about IPsec and other implementations. IPsec has been an assistant for quite some time. IPsec actually uses different mechanisms to negotiate and establish a secure either site-to-site or remote access VPN tunnel. And the protocol that is actually used to negotiate and establish that tunnel or that channel is the Internet Key Exchange Protocol, and otherwise known as IKE. IKE is a framework provided by the Internet Security Association and Key Management Protocol, or IPsec, and there are two versions of IKE. The first original version is defined on RFC 2409, and then the second version is defined on RFC 5996 and is otherwise known as IKE version 2. So in this lesson, I'm going to cover the principles of both IKE version 1 and IKE version 2, as well as other cryptographic functions of IPsec. So starting with IKE version 1, within IKE there's different phases of negotiation, and within the first phase, or phase 1 of IKE version 1, there are several attributes that are exchanged, and those are things like encryption algorithms, hashing algorithms, the Diffie-Hellman group algorithms, authentication methods, vendor-specific attributes, and some others, right? Now, there are some traditional encryption algorithms that are used in IKE, like AES, or the Advanced Encryption Standard, which you already know about, Data Encryption Standard, or DES, or Triple DES, and some other ones. Now, there are also hashing algorithms that are actually used to make sure that data hasn't actually been modified. And the two algorithms that actually have been used for quite some time is, of course, the Secure Hash algorithm, or SHA, and the Message Digest 5 or MD5 algorithm. Now, in the past, in IKE version 1, there have been two different modes for that negotiation. One is actually called IKE main mode, or IKE version 1 main mode for site-to-site tunnels, and then were typically used for site-to-site tunnels. And then there's another mode called aggressive mode, and the main difference is actually the number of exchanges and packets that are exchanged between the originator or the initiator of the VPN tunnel and the responder, right? Now, this is actually the default behavior when pre-shared keys are actually employed. First, you actually have an initiator. So in my example here, I have two routers, R1 and R2. So R1 is the initiator, and R1 has two IKE proposals configured. In the first packet, R1 actually sends its proposal to R2, and then R2 evaluates the received proposals, and because it has a proposal that actually matches the offer to the initiator, then it sends back the accepted proposal back to R1, right, in the second packet. Then the Diffie-Hellman exchange and calculation is actually started. And if you're not familiar with Diffie-Hellman is a key agreement protocol that establishes either two users or devices to authenticate each other using pre-shared keys without actually sending the keys over the unsecured method. Actually, they send something called unknowns, an unknowns payload, which is a payload that is randomly generated value, but whenever the mathematical calculation is performed in the receiver end, it matches then the pre-share key. Whenever, of course, the receiver, if it has a correct pre-share key, it can actually then verify that, and if it matches, that means that the pre-share key is the same on the other side. And then after that, R2 receives the information and reverses the equation. It basically uses the proposed diffie-Hellman group, an exchange mechanism to generate something called the S key ID. And the S key ID is a string derived from the secret material, and it's actually known only to the active participants in the exchange. Now, R1 that sends the identity information, and that fifth packet is actually encrypted already with the key material that is actually derived from the S key ID. Then R2 validates the identity of R1 and R2, and it sends its own identity information to R1. Then the packet is also encrypted. Now, a few things to highlight here. IKE actually uses UDP port 500 for communication, and UDP port 500 is actually used to send all the packets that are described in the example that I just went over. IKE also has a second phase, or phase 2, and is used to negotiate the IPsec security associations, or essays. So every time that I mention an essay, I mean a security association. And this phase is also known as a quick mode in terms, in IPsec terms. Now, the ISAK-AMP or the IKE essay, they're basically the same thing, protects the IPsec, communication, because all the payloads are actually encrypted except the ISAK-AMP header, right, or the IKE header. Now, a single IPsec essay negotiation always creates two security associations, one inbound essay, right, so one inbound security association, and one for outbound communication. Now, each of the security associations is assigned two unique security parameter index, or SPI values. Now, there are also two different protocols that are used by IPsec, AH, or Authentication Header, and ESP. And they're layer 3 protocols and do not have any port information. So, why this is relevant? Well, if an IPsec peer is actually behind a NAT device, so a network address translation device, and more importantly, behind a network address translation device that is actually doing or performing port address translation, or PAT, then the ESP or AH packets are typically dropped because they don't have any ports, they cannot be mapped, and are basically dropped. To work around this, many vendors in the past, including Cisco, used a feature in IPsec called IPsec pass-through, right? And the PAT device, that is actually capable of IPsec pass-through will build the translation by looking at the SPI values of the packets. However, this was very inconsistent. Then other vendors were actually starting to encapsulate the ESP packets, and this is only for ESP. AH will not work with this methodology, but for ESP, it will encapsulate these packets into a UDP packet, and vendors like Cisco will actually encapsulate them into either UDP or TCP. But as you can actually tell, this will be was very inconsistent across vendors. So the industry came up with a better way and a standard, right? So everybody will be on the same page, and that standard is called NAT traversal, or NAT-T, and basically it's pretty much the same. It's actually the encapsulation of ESP packets on UDP, but in this case, it's actually using UDP port 4500, right? And that allows the NAT device to successfully translate and forward the packet, and also allows for consistency among the industry and interoperability. Now, I'm going to go over a quick example of the phase 2 negotiation between two entities, right? In this case, I actually have two entities again. In this case, it's actually a couple of firewalls, right? So, and the firewalls send, or the initiator in this case, sends the identity information, the IPsec security association proposal, the nonce payload, and optionally a key exchange payload if PFS, or perfect for secrecy, is actually configured, right? And then the second, or the responder, will actually associate and evaluate the proposals against the configuration that that device actually has, and then it will send the accepted proposal back to the other firewall in this case, right? So again, it can be a firewall, it can be an iOS router, it can be any IPsec enabled device. Now, in this second exchange, it will also send its identity information, the nonce payload, and the optional KE payload for PFS or PFS if actually it's configured. Then, of course, the receiver will evaluate the proposal and it will send the confirmation that the IPsec essays has been successfully negotiated, and that will start the data encryption process. Now, IPsec can also use two different modes for encryption, either with ESP or the authentication header protocols, right? The first mode is called transport mode, and it protects the upper layer protocols like UDP and TCP. And then tunnel mode protects the entire IP packet, right? So that's one of the main differences. Now, a typical example of using, a transport mode is GRE over IPsec. And in many cases, actually, tunnel mode, so the other mode, is actually employed to encrypt and authenticate IP packets whenever they're actually originating by the host connected behind the VPN device. One thing to highlight is that tunnel mode is the default mode in most Cisco IPsec implementations. Now that we have gone over the different phases of IKE, and specifically in IKE version 1, let's go over IKE version 2 and what are the differences between IKE version 1 and IKE version 2. First, IKE version 2 is defined in RFC 5996, as I mentioned to you before. And one of the things that it does is it enhances the function of performing dynamic key exchange and peer authentication. It actually simplifies the key exchange flows and introduces, measures to fix vulnerabilities that were present in IKE version 1. Now, both version 1 and version 2 of IKE operate in two phases. You still have two phases for the exchange. However, IKE version 2 provides a simpler and more efficient exchange. Phase 1 in IKE version 2, it's basically the IKE essay consisting of the message key pair, or what we actually call IKE essay init, or the initiation. And the IKE essay is comparable to the IKE version 1 phase 1. Now, the attribute of that IKE essay phase is defining the key exchange policy. Now, phase 2 in IKE is what we actually call the child essay, right? And the first child essay is the IKE authentication message pair, and this phase actually is very comparable to the IKE version 1 phase 2. Now, additional child essay message pairs can actually be sent for rekeying and informational messages, that were not defined or supported in IKE version 1. However, these are some of the major differences between IKE version 1 and IKE version 2. First, IKE version 1, phase 1, has two possible exchanges, main mode and aggressive mode, right? Now, there's a single exchange of a message pair for IKE version 2. So there's no two different, main mode or aggressive mode, right? Also, IKE version 2 has a simpler exchange of the two message pairs for the child essay. IKE version 1 uses actually an exchange of at least 3 message pairs for phase 2. And in this case, actually, IKE version 2 has been designed to be a little bit more efficient than IKE version 1, since fewer packets are actually exchanged and less bandwidth is actually needed for that negotiation. The other thing is that IKE version 2 supports the use of next generation encryption protocols and also some new capabilities to defend against denial of service attacks. Now, despite that the IKE version 1 supporting some of the authentication methods used in IKE version 2, IKE version 1 does not allow the use for extensible authentication protocol, or what we call EAP, right? And EAP allows IKE version 2 to provide a solution for remote access VPN as well. And, it provides additional authentication capabilities. One of the things that I want to actually highlight here is that IKE version 1 and IKE version 2 are incompatible protocols. So subsequently, you cannot configure an IKE version 1 device to establish a VPN tunnel with an IKE version 2 device. So in other words, even if the devices actually support both standards, you actually have to match the version of IKE that will be used. Now here I have an illustration for your reference that it compares the attributes negotiated in version 1, in IKE version 1, in comparison to the attributes that are negotiated and the exchange, negotiation exchange of IKE version 2.